Okay, if you're taking this at home, you guys might want to pause the video for a minute and write this stuff down and draw this diagram so we can get going full speed after that. We're going to look at three things today. We're going to look at potential energy diagrams. So as the current goes around a circuit, how much potential does the circuit have after it goes through each device here that we have? So we have these little, they're light bulbs, right? Okay. And then we're going to talk about how circuits in series, the relationships between those and the circuits in parallel, which I don't have one drawn here. We'll have to draw that here in a minute. So first we're going to start with potential energy diagrams. And what we talked about is as we go through a circuit, you go from the positive end, which would be this side, to the negative end over here. And as you go through, each device that you go through is going to use up some of the potential that your battery is giving it. And so we drew one of these way earlier in the unit. But when you start a potential energy diagram, the first thing that happens is that you go through the battery and you gain all of your potential as you go through the battery. So we start at 24 volts. Okay. Then as we go through, and I've told you that there's 3 amps in this circuit, and so as we go through, we analyze this device here, and this has 2 ohms, and so when we look at Ohm's law, which says V equals I R, we have a current of 3 amps and a resistance of 2 ohms. This is going to equal 3 amps times 2 ohms is going to give us 6 volts. Okay, here in this lamp. And so this lamp in particular is going to take away 6 volts of our potential. And so we'll lose that's a negative 6 volts right there that we're going to lose as we go through that bulb. All right, then we go to the next one. Okay, we come to this guy. This is also another 2 ohm resistor. Okay, well, if the current is the same, and the current's always the same through any particular loop, okay, no matter where you are in a loop, the current is the same through that loop. This 2 ohm resistor with these 3 amps is going to give us another negative 6 volts as we go through here. It's going to take away 6 of our volts. And so we lose another 6 volts, negative 6 volts. Then we continue around. Then we get to our last device. Well, this last device is at 4 ohms. And so using Ohm's law again, our voltage across here is going to equal 4 ohms times our 3 amps for a current, which is going to be 12 volts. So here we will subtract 12 volts. Okay, well, that happens to be the rest of our potential. This is a negative 12 volts is the rest of the way down the diagram. And so this is what happens as we go around any particular circuit. We have this, we lose all of our potential by the time we return to we have 0 volts by the time we return to our battery. Okay, and this is an important relationship here, that whenever, in fact, I'll write this out to the side. Okay? In any loop in a circuit, the sum of the potentials in that circuit is always going to equal 0. Okay, so here's a plus 24, then a minus 6 and a minus 6 and a minus 12 back here to the battery again. And so that whole thing gives us a 0 when we add all of our voltages together. This would be a 24 volts minus 6 volts minus 6 volts minus 12 volts is going to equal 0 for this particular circuit. Okay. This is called the loop rule. Okay, this is the loop rule. Okay, we're going to get to another one called the junction rule here in a little bit when we start talking about circuits in parallel. Okay, but talking about the junction rule right here is kind of redundant because we don't really have any junctions. So, okay, so that's our potential energy diagram, and this this is important when we start talking about the loop rule and we start talking about the voltages in our circuit and assigning them. Which brings us to circuits in series. And that's what we have right here. Okay, and something in series okay. If something is in series, it means you don't have a choice but to go through them. If you go through one device, you must go through the other. Okay, and so with these resistors in series, if we're going to add our resistors in series, it's as if, this is easy, it's as if they were all one resistor to find out what the total resistance is between these 2 points. Okay, so if we want to figure out what is the resistance between A and B, well, because you have to go through all of them, you're going to, the electricity is going to suffer a resistance at each one of those spots. And so if we add our resistors in series, it's simply this, that our total resistance, okay, R total, equals R1 plus R2 plus R3 plus however many there are in that particular series. So in this particular case, it would be 2 ohms plus 2 ohms plus 4 ohms, which would equal 8 ohms. Ta-da! That's it. That's it for resistors in series. Really straightforward. Okay, and we can kind of check that by looking over here. 2 plus 2 plus 4 is 8. Let's say we want to find the current in this whole thing, the current back here in our original diagram. If we start with 24 volts, this can equal our current times our 8 ohm times our 8 ohm total resistance. If we want to find the current, we would divide by 8. And that would give us 3 amps. which is what we assigned at the beginning. That make sense? Destin? Tot, T-O-T, same as that. Tot, T-O-T, same as total. Okay, so that's for adding resistors in series. Then we need to talk about parallel. Okay, parallel is hooked up a little differently. And I haven't drawn a diagram for this, so here we go. Parallel is if we actually, well, draw them. If we actually draw them next to each other. Okay. In this case, you have a choice. Okay, you can go through any one of these branches, okay, to get to the other side. So here's point A. Here's point B. You can go through R1, R2, and R3. We'll call this 4 ohms, 2 ohms, and 2 ohms. You can go through any one of these to go from point A to point B. Yeah? Okay. So if you can go from A to point B using any choice, then the resistance isn't going to be the same as if you go through all 3 of them. You don't go through all 3, you only go through one of them. Okay. But, and here is where the loop rule comes in. We're going to give this, we're going to call this 4 amps. 4 amps going this way. Okay, here we have the junction rule. This is R1 equals 2 ohms. This is R2 equals 2 ohms, and R3 equals 4 ohms. Okay. So we have the junction rule, which is the total current entering a junction Okay, so the total current entering a junction equals the total current leaving a junction. So if here we've got 4 amps entering this spot, these 4 amps are going to be separated and divided up into these 3 different directions. They'll go through and they'll come back out at 4 amps still. Okay? That makes sense? All right. Now, we'll show you guys how to divide this here in a sec, but here's how we add our resistors. Now, I can go through all the math and show you how to derive how to do this, but I'm not going to do that. Okay, I'm just going to tell you how you add these together. In parallel, they don't add the same way that they added up here, where it was this one plus that one plus that one. Okay. When they're side by side, they add with the reciprocal. So that 1 over the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3 plus, and so on. Okay, and I'm running out of rule on the bottom of this page, so I need to slide back over here. Okay, so what this looks like is our total for this equals 1 over 2 ohms plus 1 over 2 ohms plus 1 over 4 ohms. Oh, too far. Follow me there? Okay. Then we actually have to do some fraction math. Okay, we can't add these straight up. We have to find a common denominator. Yeah? Nope. Not 2. 2, 2, and 4. Their least common denominator would be 4. So this becomes 2/4 plus 2/4 plus 1/4, yeah? You guys remembering how to do this? Okay. So if we add those together, we get 5/4. But this equals 1 over our total resistance. So our total resistance is really going to equal 4/5, right? Because we flip it back over. We find the reciprocal of this. Reciprocal of 5/4 is 4/5. This is our total resistance. Yeah? So this whole thing has a total resistance of 4/5 of an ohm. Yeah? Okay. So now how much current is going through each one of these? What's that? No, this is our total resistance going through is 4/5. Okay. Now, we know that any particular loop has a total voltage of 0, right? So that means that this voltage has to equal that voltage, and this voltage has to equal that voltage. So all the voltages have to be the same. You guys follow me there? Well, voltage. So here, we're running out of room here, so I'm going to recreate this. My camera resets. All right, so there's a little bit of heavier math that we have to do here, but because the voltage going through all three of these has to be the same, we know that V equals IR, so or I equals V over R. Yeah? So our current through any one of them is going to be this voltage, which we don't know. Although we can know. We can figure it. Duh. That's how. Okay. Here's our current. Our total resistance through the whole thing is 4/5, right? Yeah? Okay, so the total voltage is going to equal 4 times 4/5, which is going to equal 3.2. Trust me. 3.2 volts for the whole thing. So each one of these is going to get, so the current through resistor 1 and the current through resistor 2 and the current through resistor 3 is going to equal 3.2 over 2, right? Voltage over resistance. 3.2 over 2 and 3.2 over 4. Because it's voltage divided by resistance. You guys follow me here? Yeah? And what does all of this equal if we add these all together? 6 and 6 is 12, plus 8 is 20, right? Carry the 2. 2 plus 1 is 2. Okay, so all of our current coming out is equal to the current that we had going in. Yeah? Resistors in parallel are a bit more tricky. Okay, but the thing to remember is that the voltage across each one of these has to be the same. Okay? All right, that should be enough for all of them for you guys to be able to knock this out. Or here's the idea of it. Now you may need to do some other, like I might give you the current and the voltage, you guys need to figure out what this other resistor is or that sort of thing. But this is the basis behind all of it. So, that was potential energy diagrams, resistors in series, and resistors in parallel. And your assignment tonight is page 9 and 10. And I want you to get started on 11. No, we're going to stick with 9 and 10.